Welcome to Dave and Dharm Demystify, a FinTech Futures podcast, helping make sense of the world of FinTech and digital finance. Please sit back and listen as the two Ds take a subject and discuss it to make it clearer and easier to understand.
Demystify.
Welcome to today's show, and today we are talking quantum computing. I have a very special guest, Yuval Boger, who is joining. Yuval, could you just give a bit of background to yourself, a brief introduction, and tell us a bit about what you do?
Of course. It's a pleasure to be here, Dave. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra. QuEra Computing is a company based in Boston, Massachusetts, not far from Harvard and MIT. And we make quantum computers using a technology called neutral atoms.
Fantastic. Well, I'm going to just jump straight in because we're going to really be talking about what a quantum computer is. And I know there's various types of quantum computer, but can we just start with the basics of what a quantum computer is?
So quantum computers are a new type of computers. They're not going to replace existing computers. They're going to augment them. So we don't anticipate running a Zoom call or doing Microsoft Word on a quantum computer anytime soon. And in a way, it's almost like the advent and the emergence of GPUs. GPUs like those made by NVIDIA have not replaced traditional CPUs, but they added new types of computational capability that's now used in very many applications. Quantum computers, quantum processing units, or sometimes called QPUs, would follow the same path. They are computers that use special properties of quantum physics to perform calculations in a different way. And the expectation and hope, and certainly the theory is, that quantum computers will someday soon be able to perform calculations that are beyond what can be done on even the world's largest, fastest supercomputer. So things that might take supercomputers millions or billions of years could conceivably one day be done on a quantum computer in minutes or hours. Not everything, but certain very important things could be done this way.
So how is a quantum computer able to do that?
So the fundamental computational unit of a quantum computer is called a qubit, the quantum bit. So just like a classical computer has a bit, a quantum computer has a qubit. In a classical computer, that bit could be either 0 or 1. So it's always 0 or 1 unless you change it. So if you put it to 0, it's going to stay that way essentially forever. A quantum computer is different. A qubit in a quantum computer could be put in a state that's almost like flipping a coin, and the coin is sort of midway in the air. So you don't know yet if it's going to be heads or tails. There's some probability that it's heads. There's some probability that it's tails. And by the way, if the coin is fair, that could be 50-50, but it doesn't have to be a fair coin. So maybe it's 79% probability once it lands on tails and 21 on heads. And if you have many qubits, then you have at the same time different probabilities. For instance, if I take 2 qubits, there's some probability that they're both in 0, 0 or heads and heads. There's some probability that's 0, 1. There's some probability that 1, 0, and there's some probability that's 1, 1. So essentially, the way a quantum computer works is that you have several qubits, the more the merrier. And the quantum program essentially modifies the probabilities. It makes one outcome more likely than the other. And that allows you to program in a different way than you program classical computers, but it allows you to sort of solve different problems. So for instance, let's assume that you have a stock optimization problem or an asset allocation problem. Let's simplify it and say you've got 50 different assets, and you need to either choose if you want to own that asset or not own that asset. So for each one, either 0 or 1, own or not own. Imagine that you could put 50 qubits, each qubit representing one of these assets, and then cause the quantum computer to increase the probability of those solutions that meet your goal, minimum risk or maximum outcome or what have you. And when these problems get larger and larger, they become intractable for classical computers. They become unsolvable in a reasonable amount of time. So the hope is that quantum computers using this method could solve this and many other problems.
So in a way, the bigger the problem, the more adept quantum computers will be in terms of the sorts of problems that it's looking at.
Yes. So one metric that's sometimes used for this is if a quantum computer is sufficiently small, if it has just few qubits, then you could simulate a quantum computer on a classical computer. Sort of an extreme example, if the quantum computer only has 2 qubits and there are only 4 possible outcomes, then it's obvious that you could simulate that on a classical computer. The nice thing about quantum computers is that as you add additional qubits, with every additional qubit, number of possible outcomes doubles. So you go from 2 to 3 qubits, you go from 4 to 8. When you go to 10 qubits, you already have 1024 outcomes. And so today's sort of fastest, biggest, baddest supercomputer could simulate a quantum computer with about 50 qubits. So if you have a problem that requires 100 qubits, it can no longer be simulated perfectly on a classical computer.
I see. That's fascinating. And so when we've talked previously with Sergey Gago from Moody's, and he talked about this Q day, which is when RSA encryption can be, there's a powerful enough quantum computer for it to be able to break the encryption. And from what you're saying, that will require a certain number of qubits in order to be able to achieve that. Is that right?
Yes, that's absolutely correct. What Sergio was talking about is quantum computers running an algorithm called the Shor's algorithm. Shor's algorithm was invented by Peter Shor, a professor at MIT, and it allows factoring very large numbers, which is the underlying principle for RSA encryption. So today's quantum computers are not there yet. So in today's quantum computer, you could say factor 15, but 15 and 3 times 5, you could do that. We could do that in our heads. We don't need a computer at all, let alone a quantum computer. But when the prime numbers become very big, that's where you need a quantum computer. And experts have differing opinion whether this is 5 years away or 10 years away, but one way or the other, it's coming. Q day is coming.
Again, you'll have to forgive me because I'm going to ask probably a bunch of very stupid questions, but the bigger a quantum computer gets, does that mean that there's the pace of sort of a possible future where you can get to Q day speeds up as well? So if you get bigger quantum computers, can they, I don't know, work with AI and machine learning in order to sort of help you build more powerful quantum computers? And so I don't know if that's a good question or not. So you'll have to forgive me.
No, this is an excellent question. Quantum computers are believed to be able to solve 3 main classes of problems. One is optimization, and we spoke about portfolio optimization, but there could be traffic optimization, or there could be supply chain optimization, and so on. The second thing is simulation, meaning chemical structures, for instance, or vaccines, or chemical compounds. So when you say, is it possible to develop a better solar cell that's more efficient? Or is it possible to develop a better battery for an electric vehicle, something that has more capacity or that weighs less or that is easier to make? You're looking at chemical simulations, and that quantum computers could definitely help there. And the third area is machine learning, which is another area. Now, it's not as if in 2 years, all of a sudden there's going to be a quantum computer that's going to be good for all of these problems. Some problems are more difficult than others. There are algorithm developers that work on trying to fit algorithms into existing quantum computer. Even Shor's algorithm that we discussed earlier, since it was published, there were a couple of researchers that said, well, here's a way to implement Shor's algorithm with fewer qubits, which means that on one hand, the machines become better, and on the other hand, the algorithms require less. So they're going to meet a little bit sooner.
Okay, that's fascinating. One of the things I'm absolutely fascinated by is the sort of hardware aspects of this. So I guess quantum computers is dealing with things on a very small scale, like you're dealing at the atomic scale. And from what I understand, there's a number of ways of, or a number of avenues of development that have kind of taken place in terms of the hardware that's used. So can you just explain a bit about that as well? And then a bit more about the technology or the way that your company is using things at the atomic level to make calculations.
Sure. So you're absolutely right. There are different ways to make quantum computers. In the professionals, they sometimes call it modalities. There are different modalities on how to build a quantum computer. So some of the popular ones, one is called superconducting. So superconductors are materials that have no resistance, no electrical resistance, and that usually happens when they are approaching absolute zero temperature. So minus 273 or so degrees Celsius, 0 degrees Kelvin. And so the sort of iconic picture of a quantum computer is these golden chandeliers that you sometimes see. And these are actually associated with these superconducting computers. They are essentially multi-stage refrigerators, or refrigerator is probably an understatement, which cool material to lower and lower temperature, and then the quantum effects kick into place, and you can build a quantum computer this way. So these are superconductors, and a company like IBM is one of the companies that's making these type of computers. Others are saying, no, we're actually going to use photons, particles of light, and that's how we're going to create a quantum computer. In our technology, we use what's called neutral atoms. And let me explain how it works. And, the first time I came into QuEra and someone told me that story, it felt like science fiction. That can't be happening. But then over time, you just get used to it, right?
I know. You talk about that. And you're like, how did anyone ever think that what was the inspiration? How did they kind of get it? How did, anyway, be interested.
I think a lot of our scientists understand that we are standing on the shoulders of giants, that if you look in our machine, there are actually 4 or 5 different sort of Nobel Prizes in physics that all combine to make this happen. So let me explain, if it's okay.
Of course. No. Brilliant.
So our computer uses individual atoms. Each qubit is a single atom. And in our case, we use an atom called rubidium. If you remember the periodic table, rubidium is a few rows underneath hydrogen. So it's on the left side of the periodic table, underneath hydrogen. And rubidium has one outer electron. So, every atom has electrons going around it, and rubidium has one outer electron. Using laser light, we can excite that electron. We can basically move it from a ground state, sort of a low energy level, to a higher energy level. So that electron absorbs some light from lasers and moves to a higher energy level. So far, so good. So we have atoms that we can put either in a ground state or in a higher energy state. These atoms are held in place. How are they held in place? This is where the science fiction part comes in, except that it's science and not fiction. Each atom is held in place by a tiny laser beam. So imagine a laser beam that captures an atom, and it works in a way that the atom doesn't want to move away from the laser beam. In fact, when the laser beam moves, the atom is sort of trapped, continues to be inside the laser beam. This is, in the professional description, it's called a laser tweezer or an optical tweezer, because it's almost like taking tweezers and taking a single particle from one to the other.
Tweezers for one atom.
Right. So each atom has a tweezer. Now, these tweezers, most people think about, if I hit an object with laser, you think that would heat up the object. Well, one of the Nobel Prizes that's relevant to our computers is that these laser tweezers, when are correctly tuned or perfected, they actually cool the atom. They cool the atom to essentially sub-zero temperature, a millionth of a Kelvin. And so the atom doesn't really move. It sort of stays in place. Now, if I have 2 such atoms and they're far apart, they don't really care about each other. They're indifferent. They don't notice each other. But if I get them together and I try to move them into a higher energy state, sort of shoot a laser light at them so that the electron goes to a higher energy level, then they do care about each other. Essentially, if you were able to image an atom, at least conceptually, when the electron is at the higher energy state, the atom appears to be about 1,000 times bigger than it is normally. So you have these 2 small atoms, and then all of a sudden you try to puff up one of them, or what happens is they don't want to be puffed up at the same time. And this allows us to create these probabilities and the interaction between the atoms. So essentially, the process of us building a quantum computer is we first trap a lot of these atoms with individual laser beams in our existing system that's been up on the Amazon cloud for 2 years now. We have 256 such atoms that are trapped. We can then move the laser beams to get the atoms to where we want. And then we can shoot lasers at them and get them to interact. So by moving atoms around, that's how we do the calculation. And at the end, we shine a light on them and take a picture, a real picture. And then atoms that are in the high energy state show up one way, and in the low energy state, they show up another way. And that's how we know how the calculation ended. Now, remember that we spoke about coins with probabilities, 79, 21, and so on. A quantum calculation is usually repeated multiple times. So again, if I gave you a single coin and asked you, is it a fair coin? Or if not, what's the probability? You would probably have to toss it a good number of times. If you toss it just once, you don't know what that means. If you toss it 1,000 times and you get 499 and 501, then you say, okay, I think good chances are that it's a fair coin. So we repeat that process again and again. We trap atoms, we move them in place, we excite them, we take a photo, and we do that a number of times. And ultimately, that's where we get the statistics of our calculation and the final result. The science fiction-y part, if that wasn't enough, is that these atoms are, when they are excited, when they are interacting, they're about 4 microns apart, 4 millionths of a meter apart. So it's incredible that you could put tens of thousands of atoms on an area that's nothing by nothing, right?
Well, look, I mean, it's all science fiction to me. So again, this is going to sound like a really dumb question, but how do you program, how do you sort of interface with that whole process as a kind of user to say, this is a problem I want solving? So are you using a keyboard, or, what's the input mechanism for this?
Yes, of course. So you program quantum computers in quantum programming languages. There are several of them, and actually there are many companies that are making an effort to make it look as close as possible to classic programming languages. Now, if you were programming a classical computer and you go all the way down the stack, you say, oh, I have a Python program, and this gets compiled into this, and this gets compiled into assembly language. But the CPU doesn't really run assembly language. I mean, you still have transistors on a chip that do other things. So at some point, there's lower and lower layers that get it closer to the hardware. So the same thing happens with quantum. You program in quantum programming languages. So if we spoke about assembly language, then a popular quantum assembly language is called QASM, QASM, just like bit and qubit, assembly and QASM. And so you don't manually fix the lasers, you don't manually excite the atoms, but you tell the program what is it that you want to have happen, and then you have a bunch of compilers that take it all the way down to the hardware level. The calculation that I described, by the way, happens in microseconds.
Right.
So these atoms don't just like to stay in place for hours while you do your thing. So there's a lot of preparation. That's like, shh, and that's it. Then it's done, and you've got a measurement, and then you can repeat it again and again.
I mean, it's absolutely fascinating. And I mean, I'm going to have a long, hard think about what you've told me as well, because it's sort of, there's a lot in there. I guess we've talked to a few financial services companies, and if I was interested in one of them and I was interested in quantum computing, and would I then sort of think about like choosing a partner to kind of do all of this? So I guess we've got difference in hardware, you've got differences in approaches. So the question is, when people come to you and say, look, we're interested in quantum computing, can you support us? What is it that, or how do they approach that? Or are you going out and sort of reaching out to them? Is it more the other way?
We work today at QuEra, and we offer 3 main things. The first thing that we offer is projects, co-development projects, just like you described. So for instance, you mentioned Sergio from Moody's. So Moody's partnered with us a few months ago, and since then they published the results. And Moody's, as you know, is a financial services firm that has other financial services firms as clients. They provide information to them. And some of their clients are insurance companies. And insurance companies care about risk. One major hit for insurance companies is hurricanes or tropical cyclones or sort of severe weather events. So Moody's did a project with us to say, could we use QuEra's quantum computer to make better prediction for the severity of a tropical cyclone? So you have a storm that's coming. Okay, is it going to end up being category 5 type damage or category 1 or anywhere in between? If I were an insurance company, I would want to know. I need to get adjusters ready. I need to make sure I have money to cover the claims and so on. So that's certainly an area. Now, Moody's has expertise in the data that they have. Can you tell us about hurricanes? How can we teach a quantum computer? They also have a very good understanding of quantum computers. And we at QuEra have both a fantastic application development team that can work with a customer, as well as superb hardware that can execute that. So the ideal team for such a project is someone who understands the problem. Could be, is it a value at risk problem? Is it a portfolio optimization problem? Is it asset allocation? What is the problem?
I think there's another example. It is sort of fraud analysis, I guess, is another one. Where
fraud analysis. Are these transactions kosher or not? And what does it tell us? You could say, I want to develop a machine learning algorithm that matches this, I think MasterCard has done, that matches the best offer for a credit card to a consumer. You're a credit card consumer. MasterCard is not going to offer you 100 different offers. It tries to offer you a few that fit what they believe is good for them and good for you. So that's one thing that we would do.
Yeah, no, well, I mean, that's incredibly. So I guess if you take the hurricane example, so you've got them coming to you with this is the problem. Here's data, lots of data or access to lots of data. But what we want to know is essentially, how do we predict what is going to happen based on that data? And you are then in a position where you can say, well, actually, this is how we'll set up the kind of computational program that will sort of find the answer to that. Is that right?
Yes. I mean, we said, well, these are some of the projects that we did in the past. These are some of the algorithms that we use. Let's try them out. Now, we spoke earlier about simulating the behavior of quantum computers on classical computers. So what often happens is once we have a candidate algorithm, we run it on a simulator. So we have a simulator that maybe supports 20 or 30 or 35 qubits that you could run on your desktop computer or on a server that you have. And if you're comfortable with the results, now you say, okay, now let's see what happens when we run it on 100 qubits, and that you can only do on the physical machine. So yes, hurricane is one example. Another example that we did with an energy company is try to optimize the location of EV charging stations. So you own a bunch of petrol stations. You say, oh, I hear this EV charging is a good thing, but I don't want to it's expensive to set up. I want to put only a certain numbers. I want to put them where the Teslas are. I have some ideas or what's best. I don't want to put two stations that are too close to each other because I'm sort of spending double and not getting a lot of benefit. How do we optimize the location? So this is a problem that we solved with the quantum computer. And we have several others that we can say, here are all these optimization problems or machine learning problems that we've solved. These are all part of our sort of professional services or application code development offering.
Fantastic. So you were going to talk about the next thing that you do as well, which is...
Sure. So the second thing that we do is we offer access to our computer via the cloud. So for 2 years now, we've had our 256 qubit computer on AWS Bracket. That's the Amazon cloud service. And we've had people like JP Morgan or like BMW that may need some help from us, or maybe they're just experts enough on their own and they just submit jobs to the cloud and get results. That computer is available today over 100 hours a week. So there's almost no excuse for not using it. Anyone with a credit card anywhere in the world could set up an account and submit a job. There are tutorials. So you can get started very inexpensively on a real high-end quantum computer.
Wow. Wow. So, I mean, as you say, there's nothing to stop anybody or any company who might be interested in the app from just giving it a go.
Absolutely. And the third thing that we do is actually sell computers. So there are organizations, companies that actually want to have their own quantum computer. Now, why would you want to have your own quantum computer? There could be a number of reasons for that. One is that you want to run jobs that you just don't want to have on the cloud. If you're a high security government agency, or if you're developing the next big breakthrough in material science, then maybe I just want it in-house. The second thing is, and we see that with GPUs and AI. Once AI became so popular, there was all of a sudden a shortage of GPU resources. So people said, if it's the same thing happens in quantum, I don't want to get caught where I'm not going to be able to run my quantum job just because there's a big line, the big queue of people want to run it. So if I have my own computer, I can do that. The third reason is a lot of these quantum calculations also use classical computers. For various reasons, you have algorithms that sort of ping pong between a quantum part and a classical part back and forth. If your quantum computer is co-located with your classical computers, then that could happen very quickly. There's very little latency as opposed to shipping the data from across the globe. And the fourth reason is a lot of countries and a lot of regions have identified quantum as the next strategic technology. They want to make sure that they have expertise and workforce and companies in their country that do that. So I know you're speaking from the UK. One of the agreements that QuEra signed is to deliver a quantum computer, a quantum testbed, to the National Quantum Computing Center in Harwell as part of the UK National Quantum Program. We also signed another deal to deliver one to the National Institute of Standards in Japan, AIST. So we sell computers, we provide cloud access, and then we provide co-development services.
But if someone, I mean, you mentioned Harwell, which isn't too far from where I'm sat today, actually. It's known for being a place where kind of science happens. If you were to buy a quantum computer, that's not just like buying another laptop. You're talking about very sophisticated laser and atomic technology. What does it look like? Does it come as a sort of big white box? Or, I'm just sort of interested in what it kind of looks like.
So we spoke about different modalities for different quantum computers. So they look different. Some modalities, like superconducting, are really solid state machines. Other than the cooling system, it's essentially a rack with equipment in it. In our system, because there are lasers and lenses and all kind of things. By the way, there's a media kit page on our website, QuEra.com, where you can see some pictures of what this actually looks like. We have a container where we ship the entire machine. Then we have some of our people assemble and integrate it to make sure that it works as specified. And then, as you mentioned, it is a complex device, both on the hardware and the software level. And so as part of selling a computer, we also provide on-site service and support, both to make sure that the machine keeps running as intended, as well as to help your application developers and scientists make the most out of this amazing machine.
Fascinating. One area which I did want to touch on was energy consumption, because I was looking at a graph over the weekend, which is actually, in a way, shocking in terms of what it was showing in terms of traditional computers, data centers, and GPU, how hungry they are for kind of energy, and not just energy, water as well. Are quantum computers going to add to that problem? Or if they've got tiny lasers and things, it sounds like they might be using a bit less energy. So I was just kind of interested in your perspective on that.
Quantum computers use dramatically less energy than classical computers. So if you look at the top supercomputers, they use megawatts and megawatts of power. And you may have heard that companies that are setting up large supercomputers for AI are actually starting to think about building their own nuclear power plants
I've just been reading it. Absolutely.
To power that. So they use megawatts and megawatts, which means millions and millions of dollars, pounds, or whatever currency you're using to power that every year. Our quantum computer, so I was mentioning the one that's available on Amazon Bracket. It has 256 qubits. There's a small subset of problems that it can solve better than any supercomputer in the world today. That computer takes 7 kilowatts of power. 7 kilowatts of power is like 3 hair dryers.
Oh,
Yeah, I could theoretically install one in your living room, and your house certainly has enough power to support 7 kilowatts.
isn't that enough excuse for the big tech companies to say, well, actually, we need to invest all our energies in this? Because, as you say, it's kind of, if the other alternative is nuclear power for data centers, it sort of feels like that's not sustainable in its own right. So something which uses a hairdryer's worth of electricity sounds like a much better thing.
Yeah, and I think that's part of the ROI, because people would say, if your quantum computer, the existing one or the one that you're developing now or in the one in 3 years, even if it could take just 10% of the computational load that I'm running on classical supercomputer and save all that energy, it almost pays for itself just by the energy saving, not to mention that you're able to solve problems that you couldn't solve before. The impact of quantum computers on energy is even beyond that, because we spoke about designing new materials for better batteries, better solar cells. One of the famous optimization problems that could be solved with quantum computers is what's called the traveling salesperson problem. You have a FedEx truck that needs to make 100 stops to deliver packages. What's the right sequence of stops? If FedEx were tomorrow using a quantum computer that saved them 20% on their fuel consumption just because you found a better route, that by itself gives them both a huge competitive advantage as well as a big saving in their energy budget. So absolutely, we believe that there's a very positive impact that quantum computers could make on energy consumption.
Absolutely fascinating. Well, listen, time's run out, unfortunately. I mean, I could literally talk about this all day because it's such an interesting topic. A question for you as well. It sort of feels like quantum computing has gone through that sort of hype cycle. It's kind of come out the other end. It feels like there's a sort of normalization. This is now something that is strategically important for companies to really be thinking about. So as a sort of closing thought, do you think that's a fair comment?
Absolutely. And I think quantum computers some time ago moved from if to when. If as in, could you actually get one to work and do something useful, to when can I get true business value from it? I think there's little doubt that quantum computers work because there are plenty of manufacturers with different types of quantum computers, but you can run a quantum computer today and more than one and verify the results, and they're all there. Now, there's still problems to solve, right? Quantum computers need to be bigger as it relates to the number of qubits. They need to be a little bit more resistant to environmental impact so that you can run longer calculations. But companies like QuEra and others are working really hard at that, usually in our case together with MIT and Harvard, and other cases with other leading academic institutions. And we believe that in just a few short years, some businesses will be able to take true advantage and receive true return on investment from using a quantum computer.
And just, I guess, one final thing, quantum computing it's not a new thing. I mean, the quantum as a theory goes back a long way, doesn't it? Like, I think sometimes we sort of listen to it and go, oh, this is brand new, but it's not actually, is it?
You've used ChatGPT before, I'm sure. ChatGPT is an overnight sensation, 50 years in the making. I mean, right. Machine learning and AI has been worked on for decades until all of a sudden there was a point where you say, oh, now there's this, what people sometimes call the ChatGPT moment. Well, quantum computing has been worked on for decades. I mean, Richard Feynman suggested a method that's essentially what we do today in 1982 in a very famous NASA presentation. So now, 40 years later, it's coming into reality. And it is emerging from the shadows of, oh, just a few geeks are working on it, to becoming a true industry with a dramatic global impact.
No, very interesting. Well, listen, thank you so much for joining us. I'll make sure that we put a link to your website in our notes for the podcast as well, so people can have a look at what a quantum computer actually looks like. But it's been really helpful for me, and I'm sure for our listeners as well. So thank you so much for joining us.
Thank you very much, Dave. And you asked some wonderful questions, and glad to be here in the future to talk about whatever development comes between now and then.
We will definitely be back in touch.
Thank you for tuning in to Dave and Dharm Demystify. We hope you enjoyed the show. Don't forget to like and subscribe, and tune in next time as we take another topic and demystify it.